The primary use case right now is like L2 preconfirmations and base Rollup preconfirmations.
The only credibly neutral, shared, and decentralized sequencer that I know of is Ethereum itself.
I had like kind of goosebumps when I was writing it. Like as Justin was mentioning, it's like the Ethereum is like the internet computer and the internet finance.
I believe, the future of Ethereum is extremely bright.
EIP-7917 is a relatively simple change. Like I was able to explain it in like 3 slides.
The traditional world of finance will migrate on-chain, specifically onto Ethereum.
Hello everyone, welcome to PEEPanEIP, the podcast where we explore Ethereum improvement proposal and learn what's ahead for the Ethereum ecosystem. This is episode 146, brought to you by ECH Institute. Today, we are diving into EIP-7917 Deterministic Proposal Lookahead, a protocol change designed to pre-calculate and store a deterministic proposal lookahead in the beacon state at the start of every epoch. The proposal was documented in March 2025 and currently is in the draft status. It is also up for Fusaka upgrade. To provide an overview of this consensus layer improvement proposal, we are joined by co-author Lin Oshitani and Justin Drake. Welcome, Lin and Justin, to PEEPanEIP.
Yeah, thanks for having us.
Thanks for having us.
Thank you both for joining us here today. So today's talk is divided into 4 sections: introduction, presentation, Q&A, and rapid fire round. So if it is all right, maybe you can share a bit about your professional background, how you discovered Ethereum, and what project you are currently working on.
Yeah, I can start. I'm Lin. I work at Nethermind. I do protocol research, and I've been working around Ethereum for over a year now. I've joined Nethermind, and that was my first Ethereum job. And yeah, before that, I used to be core dev for another blockchain called Tezos. And yeah, but I thought Ethereum seemed very interested and wanted to join. So yes, I'm here.
And I'm a researcher at the Ethereum Foundation. I've been there since 2017. And before that, I was into Bitcoin, discovered Bitcoin through Dankrat of Danksharding fame in 2013, and bought my first Bitcoin through him. We ended up operating a Bitcoin ATM together. I also started the Cambridge Bitcoin meetup group and also started a Bitcoin startup, building a peer-to-peer marketplace on top of Bitcoin. But ultimately, I found Bitcoin frustrating and inadequate to build a peer-to-peer marketplace on. And that gave me an interest to go discover and learn more about Ethereum.
Pretty interesting backstory. We are happy and so honored to have you both here today to talk about another Ethereum improvement proposal, which hopefully will make Ethereum consensus layer even more smoother. So with introduction out of the way, we can jump right into the EIP. Without further ado, let's peep in.
So I guess I'm happy to provide a little bit of context here. So I guess there's 3 things that we're trying to do with Ethereum. First of all, we want to try and provide a very robust and secure platform. And this is what I've been spending almost all of my time as a researcher, trying to make Ethereum more secure. And this is part of what my research with the Beam chain is also all about, improving security. But beyond security, there's basically 2 features that we want to work on. One is increasing throughput, basically scaling. And we have lots of ideas with rollups and data availability. And there's a whole program there around danksharding and PeerDAS. And then there's another idea, which is to try and reduce the latency of user transactions. And here we basically have 2 tools at our disposal. One is to reduce the slot duration, or 2, kind of a more recent idea, is preconfirmations. The idea of the preconfirmations is that you keep whatever slot duration you have in your decentralized sequencer, and you make use of the fact that the current proposer that has sequencing rights for the current slot can make promises about the transaction that they will include at the end of the slot. And from the perspective of the user, as soon as they get that promise, it's almost as good as if they had their transactions actually included on chain. And part of the reason why this promise is so good is because it's backed by collateral. It can either be backed by financial collateral, or today what is very common is being backed by reputational collateral in the case of centralized sequences. And we also have designs out there that make use of SGX, where you're using secure enclave to have credible commitments about your preconfirmations. Now, my hope was that we could do preconfirmations without any hard fork on Ethereum L1. And that's technically true, but it turns out that there is an edge case. And the edge case has to do with the proposer Lookahead, which is that in order for a user to receive a preconfirmation, they need to know who the next proposers are going to be. But in this one edge case, the future proposers, also known as a proposer Lookahead, is unknown. And that causes all sorts of complications and makes the designs for preconfirmations unnecessarily complicated. And I give all of the credit to Lin for basically identifying the problem, coming up with a solution and basically driving the process of this EIP forward. And he's the one who can answer all of the technical details about the EIP.
Thank you so much for setting up the stage. So with that, we can perhaps get into the presentation.
Yeah, today I'm going to talk about EIP-7917, Deterministic Proposer Lookahead. And this is by me, Lin from Nethermind Research, and Justin from MIA. So the outline is this. So I heard this is more of a educational session. So first I'll cover a lot of the basics about based rollups and preconfirmations. I think Justin gave a good overview, but I'll go into a little more of the details. And yes, I'll talk about two issues around preconfirmations that are related to the lookahead, like lookahead access in the EVM and the lookahead instability. And then I'll dive into the details of the EIP. Okay, first, some background. So what are based rollups and preconfirmations? But even before that, let's talk about what rollups are. So rollups are a technology for scaling Ethereum by posting transaction data to the L1, but executing them in the L2. So what this means is that the L1 blocks contain L2 blocks like this. So you have the L1 block, and then within the L1 block, you have this small this L2 block included within it. And the core thing here is that the L1 block, the transaction data itself is included in the L1 block, but the L1 validators don't execute this L2 block part. So this is where the scalability of rollups come from. But one of the big questions here is who builds these L2 blocks? And it's kind of natural that this becomes a central issue in L2s, because if you look at L1, if you look at ETH research, most of the question is about how do we build these L1 block? So it's only natural that in the L2 context too, the big question becomes who builds these L2 blocks. Okay, so the answer right now is for most of the major rollups where you have centralized sequencers who build the L2 blocks. How it works is like this. You have a centralized sequencer in the network, and these are some server run by some foundation. And the users will send their L2 transactions to the centralized sequencer. And then the centralized sequencer will aggregate all these L2 transactions and post the L2 block through the proposer to the L1. Yeah, and centralized sequencers are really great. They can provide what's called preconfirmations. So what are preconfirmations? Preconfirmations are this. So let's say that you're a user and you send transaction C to a centralized sequencer. Now what the centralized sequencer can do, it can immediately return what's called a preconfirmation. What this preconfirmation is, it's saying that I will promise to include your transaction C, at the third position in the L2 block after transaction A and transaction B, for example. Now, some time passes, centralized after this preconf is made, and then eventually this centralized sequencer will construct an L2 block, post it to the proposer, and the proposer will include it in their L1 block. And this L2 block that's included within the L1 block, it will include the transaction C in the promised position. So the nice thing here is you don't have to wait until this whole thing is built to know how your transaction is executed, because you can have this immediate preconfirmation. And yes, centralized sequencers are great. They bring fast UX, which is, I would say, critical for mass adoption. However, one big problem here is, as you can see from the name, they're centralized. So the big question is, how do you decentralize the centralized sequencer? And here's where base rollups come in. So the idea of base rollups is like surprisingly simple. Like the problem here was that you have a centralized sequencer that sit in the middle that is centralized. So let's just remove this entity. And let's just say that like the L1 proposers sequence the L2 blocks. So not just L1 block, but also the L2 blocks. And yeah, base rollups are really nice. They inherit the L1 censorship resistance and liveness because like you don't introduce any of like additional bottlenecks to the whole system. Like all you have is a plain old like L1 validator set. And also like they enable what's called L1 composability, meaning that like you can have composable transactions that goes between the L1 and the L2. So you can have the L1 and L2 like interact in a much more seamless way. And this is possible because like this proposer, the L1 proposer, is now sequencing not only the L1, but also the L2, meaning that like they can act as kind of like the shared sequencer for both the L1 and the L2 and provide composability guarantees. Okay, base rollups are nice, but there's one problem, and they're slow. Like they must wait until this L1 block is actually built to know like how your transaction is executed, which means that we must wait until the L1 block time, which is currently 12 seconds. The big question here is, how do we make them faster? Like how do we like have good UX in a base rollup setup? And here is where based preconfirmations from Justin that was proposed from Justin comes in. And the idea is this, like who is the entity who can provide preconfirmations? It's actually, if you look at it, the L1 proposer, they can provide preconfirmations because they do have the ability to like give promises and eventually include it in the L2 block. So the idea is have the L1 proposer provide the preconfirmations. Now, one thing to note here is that we need the proposers to explicitly opt in since they need to be exposed to disincentivize equivocation. What I mean by this is like when you had a centralized sequencer, that's run by some foundation, like Optimism Foundation or Arbitrum Foundation, like they have very high reputation. So like you can kind of trust them to not equivocate, meaning that they would provide a pre-confirmation, saying that I'll put your transaction in split position in the L2 block. But eventually when you post L1, like you don't post it that way. You can post it in a completely different position or not post it at all, for example. And the thing is that for when you are a base rollup, the L1 proposers, like they're not to be trusted because there isn't reputation because they're decentralized. What you need is slashing conditions. So like instead of relying on reputation, like you rely on slashing. You say that if your base preconfirmation proposer, if you equivocate on the preconfirmation, you get slashed, and you get slashed by proving the fact in L1. And this all means that you need the proposers to opt in to become a preconfer. So how this looks like is this. So let's say that we are in like P1, a slot where the P1 is a proposer, and P1 is like constructing the L1 block right now. Now, as a user, like, but let's say the P1 and P2, like these two proposers, are non-preconfers, so they're not a preconfer, and P3 is a preconfer. Now, what happened is that the users, like, they cannot get preconfirmations from P1 or P2 because they're not like opted in and they're not exposed to the slashing conditions. So as a user, what you have to do is you have to look into this proposer schedule and say that, hey, the next opted in proposer is P3. So I'll send my transaction to P3 and then I'll get my preconfirmations. So yes, they have to send the next opted in proposer, which we call the preconfer. And what happens eventually is that like the time will come for this P3 to actually propose an L1 block. And at that time, the L1 block, they will propose an L1 block that includes the L2 block containing the preconf transactions in the order that they actually preconf. So like one of the key things here is that like for base preconfirmations, it is important to know the proposer schedule. That this proposer schedule is called the lookahead. So like as a user, you have to know like who's the upcoming proposers. So you can actually route your transactions to the next opted in proposer. Okay, so this is like the context around base rollups and base preconfirmations. Now let me talk about like some of the issues that we have with the current L1 and the lookahead. Okay, the first issue I want to talk about is like the lookahead availability in the EVM. But before that, like let me give some more context around the proposer lookahead. So in current Ethereum, the proposer lookahead is like this. So at the start of each epoch, And epoch is like 32 slots. So how Ethereum works is you have like many slots, and for each slot you can propose one block. So there's going to be one proposer and one like block being proposed. And with 32 slots, you call it an epoch. So at the start of each epoch, we have visibility of 2 epochs worth of proposers in the current L1. This means that you always have at least 32 slots worth of look ahead. So like at this point, at this like start of the epoch, let's say P0, at this point you have visibility against like all these 64 proposers. And this like epoch will like continue. And when at this point, at the slot of proposer 31, like you have a look ahead of 32. So you'll have at least 32 worth of look ahead. And here it's actually a critical kind of, as in like, this is not completely accurate. Like there is an edge case, but for now, like let's think of it as this. Okay, so like this is, you have this look ahead, and one thing that base preconfirmations or base rollups with preconfirmations want to do, we want the L2 block inbox contract to limit block submissions to the next opted-in proposer in the look ahead. What I mean by this is like here you have P3, and like whoever can construct this L2 block, it has to be limited to this guy. You don't want P2 or P1 to like just inject this L2 block in the L1 and like propose blocks, because like that will damage the pre-confirmation that this guy is proposing. Like he's saying that like include your transaction in specific position, but if this guy just proposed their block, it kind of like ruins that pre-confirmation. So you want to limit the pre-confirmation to be only able to provide by this guy, P3, this pre-confirm. So how you do that is you want to limit it in the L1. So you want, and how you limit in the L1 is that like the L1 inbox contract, or the L2 inbox contract, which is where you actually post these L2 blocks in the L1. Like you want to do something like this. So you want to fetch the next preconfer in the lookahead. So you have lookahead.next preconfer, and check that the entity who called this proposed batch, so message.sender of this function, is the actual preconfer. Now, the big question here is like, how do you implement this like get next preconfer function? And the issue here is that like in the EVM, only past proposers are visible via historical beacon routes. Current and future proposers are not accessible. So let's say that you're in this slot, like you can know that my historical like past proposers were this guy and this guy, but in the EVM itself, like you don't know who the proposers are for all this duration. Like off-chain, you wouldn't know, like because as I mentioned before, like you have the look ahead of like 2 epochs, but on-chain within the EVM, you don't know like what the proposers are. So you cannot do like this check easily. So to overcome this issue, like you need some hack, or like you need some way to make the EVM like know the look ahead. So one scheme that we have implemented is what we call an optimistic look ahead scheme. And this is what we implemented for the Tycho Nethermind preconf work. Our team worked on in collaboration with Tycho. Like what we do is we have the first preconfer of the epoch optimistically post look ahead for the next epoch to an L1 contract. So if you're like, let's say that this is the first preconfer in this epoch, he will post the look ahead epoch, the whole look ahead, to an L1 contract. So because it's posted to a L1 contract, the L1 will now have visibility against the look ahead. But this is optimistic, like because like the L1, there's no way to check directly that this is correct because again, they don't have visibility against the look ahead. So what happened is that the submitter is retroactively slashed if the look ahead is incorrect. So what they submitted here is this is incorrect. Retroactively, when like this epoch ends, like at this point, you can retroactively slash like check whether this look ahead was actually correct or not. And you can check because like as I mentioned, like historical proposers, this is available in the EVM. Okay, so like we had to implement this kind of hack, and yeah, this was one of the pain points, but it was kind of like yeah manageable in a sense. But now here comes like another issue that we found, which is called the lookahead instability issue. Okay, what this is that like I mentioned that you have 2 epochs worth of look ahead at the start of the epoch, but this is like not completely accurate. And one thing is that there's an edge case, and this edge case is that like this look ahead of the next epoch, like that you have access to or like have visibility against at this like epoch boundary, it can change in certain edge cases. So like thought that it was proposer 33, but it can change to proposer 33 prime. And what this edge case is, like to understand this, you will have to actually understand how the lookahead is actually calculated. Okay, so like how is the lookahead calculated in the Ethereum L1 protocol? And here, like two factors are used to calculate the lookahead. One is a RANDAO. So this is like a randomness seed that's available in the L1. This is like a source of randomness, let's say. And another factor is the effective balance, so EB, of validators. This means that like each of the validator, they'll have to deposit into Ethereum to actually become like a validator. And this effective balance is basically like the amount of balance that, well, they have deposited and is used when you like what the Ethereum sees as their balance is. And this balance is important because like whether you're a proposer or you are like will be proportional to how much effective balance you have. Okay, so let's say that like to understand how the lookahead is calculated, let's think of this like epoch. How is this lookahead calculated? And first, like, so there's two things, the RANDAO. The RANDAO, like, which RANDAO was used, like, is one question. And the RANDAO used is like what's available, the RANDAO that's available at this epoch boundary. So at this point, like the randomness seed to calculate this epoch's lookahead is already available. So this is why like we can say that you have two epochs worth of lookahead, because like the randomness is already like determined at this point. At this point, you have the randomness seed to calculate this part. However, like RANDAO is not the only input here. Actually, you also need a like effective balance. And the thing is that effective balance is used from here. So what's available here. So like whatever the balances of all the validators are at this point is used to calculate this lookahead. Now, as you can see there, like there's a mismatch between these two, right? Which namely, like the effective balance can change during this epoch. And this is like the source of the instability that we're talking about here. Because the randomness is already determined, the RANDAO is already determined, but the effective balance of the proposers that were in this lookahead can change. And they can change in a way that like will change the lookahead, because these two are the input to calculating the lookahead. And they can change in ways and like as a result of changing, the proposer can change basically. And one thing here, or like how this can change is important. And one thing to note here is the unpredictability is worsened due to the increase of max EB, EIP-7917, as the EB of active validators can now grow beyond 32 ETH. So before, like mostly like the EB of validators, they're like pretty stable, or like very stable, I would say, because like every validator, you can only have 32 ETH. Like the effective balance is capped to 32 ETH. Even if you're like have some proposer rewards or attestation rewards during this epoch, and it won't affect like the effective balance, or it won't change the effective balance during this epoch because like it's capped to 32. However, with the max EB change, like now the cap of 32 ETH is removed, which meaning that like if you attest or propose during this epoch, like as a result, it can change the lookahead of this epoch. So like this is like one of the sources of the instability that like increased with max EB increase. Okay, so like one question here is like, is this really an issue? Because like from preliminary analysis, like lookahead change due to EB change like remain rare. Like they are much like more possible than before when we didn't have the max EB increase. But it is like still very rare because like attestation rewards are not that much. And like the condition for this to happen, like you have to actually bump the attestation, like the effective balance enough so that like you actually be able to affect the lookahead here. But like the thing is here, and like yes, is that even if it is rare, the rewards based lookahead changes are not provable on chain, like unlike slashing, which is like another source of effective balance change. So consequently, the optimistic lookahead scheme breaks as we risk incorrectly slashing the honest lookahead submitters. So like even if it's like very rare that like this kind of thing actually happens, like where the proposer lookahead changes, like when it happens, like we don't want to be slashing like an honest entity, like that's very bad, and that will disincentivize like adoption of preconfirmations, at least in this design. So yes, it's still an issue even if it's rare. Okay, so those are the two issues that we had around the lookahead, and here comes the EIP, which is EIP-7917, the deterministic proposer lookahead. Okay, so like the idea here is very simple actually. Like as I mentioned here, like what we have is this, like RANDAO is used from this epoch boundary, effective balance is used from this epoch boundary, and there's a mismatch between this. And this mismatch is the cause of the instability because the effective balance can change during this epoch. So let's just do this. Let's say that in this epoch boundary, let's use a RANDAO from here, and also the effective balance, let's use the values that are available here. So you align these two, and based on like that, you calculate the lookahead here. And like how we do this is that we have introduced a new field in the beacon state. The beacon state is like the state of the consensus layer, basically. So it stores things like what the current slot is, or like what the validator, like set of validators are, for example. Anything needed to like calculate the consensus is stored in the beacon state. And what we do is we introduce a proposer lookahead field in the beacon state, and we pre-calculate and store the next epoch lookahead at the epoch boundary. So we add this field here, and we pre-calculate it at epoch boundary. And like one thing to note here is that because we added this to the beacon state, it is accessible via the EVM, in the EVM via the beacon root, because the beacon root, which is like the root of this, the beacon state, is accessible in the EVM. Okay, and a little more on like how we actually calculate the lookahead is that at the start of each epoch, the proposer lookahead is updated by shifting out the previous epoch's lookahead and appending the new one at the end. So before the epoch boundary, let's say that like in this field, you have like 2897, 63, and like this kind of like lookahead. These are like IDs of the validators. And when you pass the epoch boundary, what happens, or like at the epoch boundary, what you want to do is like you would shift out, like this is the next epoch's lookahead. You would shift in like this guy's to the left and shift out this part because like that epoch has already passed. And then you'll append like the new epoch's lookahead at the end. And yeah, that's basically, this is like the core logic of the whole EIP, basically. Okay, conclusion. So conclusion, like EIP-7917 is a relatively simple change. Like I was able to explain it in like 3 slides. And spec-wise, it's also very small. Like it's like 22 lines of spec change, ignoring the comments, but have like large benefits. Like first and foremost, like it unlocks robust preconfirmation protocols by making a stable lookahead that is available in the EVM via the beacon route, which completely removes the need for hacks such as the optimistic lookahead scheme that we introduced before. Furthermore, like it simplifies the proposer scheduling protocol, like in general, in the Ethereum protocol, which simplifies the security analysis and the consensus layer, like client code. Because like you remove this like specific edge case where like the proposer can change in the next epoch. And in general, it just like feels natural, I would say. Like it feels like a natural change. And to like back this final point, I would just want to share one quote here. Like this is one quote from Danny, who is like the core architect of like the POS Ethereum. And he's saying here that like it's a discussion about this like lookahead instability. And he's saying that it was a misguided design decision to give like less lookahead on proposers, but in fact, it just makes an edge case prediction in near zero cases, but one you still have to account for. And this edge case is exactly like this effective balance changes that can happen. So yeah, and yes, he's saying that it's misguided, which like backs this like feeling natural part. Okay, that's my presentation. And yes, if you have any questions, feel free to ask.
Very well. Thank you so much for this presentation. I really appreciate you sharing with the big picture, like providing context on what is the issue, why this proposal is there in place, and also explaining how look ahead is actually calculated. I'm sure that that will bring us to a few more questions. I already see there is a question in the chat here by Alex. Alex, would you like to read your question?
Hello, yes, sure. So my question is actually what pre-confirmation times can we, as users, expect in real world conditions? And if you want to go to dive deeper, what different factors or what are the primary factors that could dictate the the actual latency?
Like, that's a good question. And I think it really depends on like this pre-confirmation protocol that you build. But like theoretically, you can just be like speed of light, basically. Like this pre-confirmation, it can happen via an RPC somewhere that you just call in and get an immediate pre-confirmation. And there can be other designs where like you can have like the proposer, like preconf, actually like not individual transactions, but like a batch of transactions, and they have like some benefits around like pricing and like and so forth. But yeah, theoretically, you can just be like a speed of light, basically. Justin, do you have anything to add?
I mean, one piece of terminology that we introduced is the notion of a tick, which is a segment of a slot. So one slot might be 12 seconds, and then you have ticks, which is the order of magnitude to do the preconfirmations by the proposer. And the tick size might be 10 milliseconds or 100 milliseconds. But, you know, as Lin said, at the very least, you need to have the time it takes for the user to communicate with the proposer and receive a response. And that's one ping time. So overall, the total response time for preconfirmation is one ping time plus one tick. And if one ping time is roughly, let's say, 100 milliseconds, and one tick is, let's say, roughly also 100 milliseconds, then your total latency will be about 200 milliseconds.
Okay, got it. Thanks.
I see another question here with Simona.
Yeah, so thank you so much for the presentation, first of all. I just wanted to ask, like, from a user's perspective, like, what are the steps that need to happen after the EIP implementation so that the faster perceived transaction times to become like widely noticeable in wallets and apps?
Yeah, so like the primary use case right now, or like at least what I had in mind is like L2 pre-confirmations and L2 like base rollup pre-confirmations. So right now this is like basically Tycho, and there's like a lot coming up right now. And like for them, I think you could basically like as soon as they upgrade and like actually integrate base pre-confirmations, and like you'll just have faster UX basically. Like you have the comparable UX as you have in like current optimism or Arbitrum, for example, like in the fastest case. And like we're not sure like if we'll immediately get there, because like one thing, as you mentioned here, is like, for example, like the wallet and like the whole infrastructure adaptation on like handling this kind of like very fast pre-confirmations. So like the approach that we're taking with Tycho is that we first start with like L2 block pre-confirmations, and L2 blocks, like this concept of L2 blocks, it already exists in like indexers, it already exists in wallets. So there's nothing new. It's just like very faster L2 blocks. So this is like a very nice first stepping stone here, because you don't need to upgrade anything in the infrastructure. You just have faster blocks and like everything just works. But yeah, once you want to get into that like 100 millisecond pre-confirmations, like that will like complicate things in a sense that like the wallets have to adapt to it, like the indexers have to adapt to it, and you need some routing protocol, so you find the next RPC endpoint and all that. I think that will take time. And
I mean, the way that I see it is that there's going to be two pathways to getting pre-confirmations. As Lin said, we can either have a rollup that starts as a base rollup and then enables pre-confirmations, for example, Tycho. But there's another approach, which is that you can take a rollup with a centralized sequencer, add pre-confirmations there, centralize pre-confirmations, and then decentralize your sequencer. And I think many more rollups are going to go down the second path. So for example, we have base, which has 1 second slots, but on testnet right now, they have 100 millisecond ticks. So within one slot, they have 10 ticks, and that dramatically improves the latency. Right now, we have Optimism, which has 2 second slots. I expect them to have pre-confirmations relatively soon. Inc, similar story. And once they've de-risked all of the infrastructure around pre-confirmations, that infrastructure is forward compatible with decentralizing the sequencer. And so I'm expecting and hoping that a lot of the rollups will choose this common shared sequencer. And in order for all of these rollups to land on the same place, I think we need a decentralized sequencer which is credibly neutral, right? If you have Optimism that comes up with its own decentralized sequencer, is Arbitrum going to opt in, and vice versa? And the only credibly neutral shared and decentralized sequencer that I know of is Ethereum itself, because it doesn't introduce a new token, a new brand, or a new security assumption. And the good news is that once we've patch this UX latency aspect with preconfirmations, it will be a relatively easy sell for the rollups to opt in to the base sequencer, and therefore have shared sequencing, and therefore unlock network effects that are otherwise not possible to have, especially through what's called synchronous composability, where one contract in one rollup can call a contract in another rollup and get an immediate response. And the typical example here is Aave, that would call another contract like the Uniswap contract in order to immediately liquidate an open position because the Oracle price has gone under the liquidation price. These kind of network effects currently are broken down because of fragmentation at the sequencer level.
Yeah, that makes sense. Thank you so much, Lin and Justin. Cheers.
Thank you for the question. My next question is with respect to the window of a look ahead. I wonder if a longer look ahead, perhaps 1 week or 1 month, is feasible or useful. Why or why not?
So yes, it is possible to have a long look ahead. One of the constraints here is that it's going to affect how fast the validators will want to exit or can exit. Because if you have a 1 month long look ahead window and you want to exit, but you've already been selected, then it's actually irrational for you to exit. And if you do exit, then it leads to mislot, which is something the protocol doesn't want. Is it useful to have a long look ahead? Yes, for 2 reasons. Reason number 1 is that you can build long dated futures. So you can think of a preconfirmation as being a short dated future, meaning that you're making a promise, so you're basically selling a future, but the future is dated, in the next few seconds. Long dated futures can be useful, for example, to hedge against the variation in the base fees. So as a rollup, I'm basically reflecting the fee that I have to pay immediately on the L1 to users. But if we had a week-long look ahead, well, the rollups could buy upfront in bulk, block space, and they could lock in a specific price that they would offer to users, and it would be stable. The other reason for having a slightly longer look ahead, maybe from 1 epoch to 2 epochs, or maybe 3 epochs, is that it increases the probability that there's at least one opted in proposer when a small percentage of L1 proposers have opted in. So this is trying to solve a bootstrapping problem. So in order to get preconfirmations off the ground with a 1 epoch look ahead, you need about 20% of the proposers to be opted in. And that's something that is definitely possible to do, and various large-ish operators have signaled an interest to opt in. But if we were to increase the look ahead to 2 epochs, that number would go down to something like 10%. And if it was 3 epochs, it would be even lower. So one of the things that I'm considering in the context of the Beam chain is, do we want to review the length of the look ahead? And I believe that Max from the Estes Relay is also working on an EIP for the Beacon chain to increase the look ahead to a few more epochs.
That is very good to learn that the present window is perhaps the optimized window as per the present scenario, and in future, if we have increased demand, this can be considered. Thank you for that. I see there is another question in chat. If you want to read your question.
Yeah, you mentioned that the main issue for the instability of the look ahead comes from the discrepancy between RANDAO and the effective balance validator. But can you recall when the URL of RANDAO comes from, please? I'm sorry, maybe I didn't follow. Thank you again for the presentation.
Yeah, sure. So the RANDAO value is taken from the epoch boundary just before P0 in the slide that Lin has open. And the way that just before the P0 here. And the way that it works is that P-1, the entity before P0, if they do produce a block, they reveal what's called a RANDAO reveal, which is basically a secret that only they know and the rest of the world doesn't know. And then that revealed secret is mixed into what's called the RANDAO mix. So you basically hash in secret value. And so assuming that P0 has not previously revealed their secret to the world, the RANDAO mix at the epoch boundary is unpredictable to the whole world, except for P0, who would know what this random value is. But I guess the way that RANDAO is generated in some senses is a detail that is not super relevant. Like, the important thing is that there is a mismatch between the RANDAO value that's used, which is at the epoch boundary before P0, and the effective balances snapshot that is being used, which is the one before P32. And I can tell you that as designers of the beacon chain, the intent was not to have this discrepancy. So this is definitely a bug that was discovered post facto. And Lin's EIP is a fantastic and very simple solution to the problem.
And on top, I would like to add, if people are interested to learn more about RANDAO, I believe there is an episode done by Mikhail Kalanen at the time of merge, where he explained the calculation part of it as well. So people can also watch the conversation over here. Hopefully that will be helpful. All right, I have one more question with respect to the proposal. When we have any consensus layer proposal, especially on CL side, because that is related to like carrying money, carrying ETH, validator and all, there are some consideration about the possible attacks. I wonder what types of threats like DDoS or proposal collusions were considered, and how does this EIP mitigate them?
I would say that this is actually a common question, so thanks for asking it. And one of the concerns here is that you have to look at it deterministic for 64 slots. Wouldn't this be a DOS vector, because you have this whole lookahead that's available? And the thing here is that this EIP doesn't really change the lookahead, the available lookahead. Right now, it's already this 2 epochs worth lookahead is already available for anyone in the network. It's just that one, it's not available in the AVM, and 2, it's in certain edge cases it can change, but it is an edge case, so you already have a very, very high accurate approximation of what the lookahead is. So whatever DOS vector that you have through this a lookahead, it's existed before this EIP, and after this EIP it will not change. But this EIP is definitely not worsening the situation there.
Yeah, this entire EIP is a result of an edge case.
Yeah,
so
exactly.
That is great. I see one more question in chat. Titi, if you would like to read the question for the guest.
Oh, yes. I wanted to ask if there is any edge case in which an L2 block would be full so that a user can't get a preconf during that current slot.
Yeah, that's also actually a very good question. So I think if this L2 block can be full, so you cannot no longer provide preconfirmations here, right? And this can be one way to mitigate this, is that this preconfer who is ahead, not far, but in the future, look ahead. This guy can actually post the L2 blocks early on in B2 or B1 through the public mempool or through some builder RPCs. And by doing that, they don't have to just fit all the L2 blocks in this specific part of their L1 block. They can spread it out into these different blocks. Especially important when the preconfer is pretty sparse, and for example, one preconfer has 10 or 20 or 30 worth of slots to preconf for. They would want to spread out the L2 block inclusion throughout the slots that they are allocated to. And that way they prevent the fact the situation where they just can't fit the L2 transactions.
I mean, the other thing that I'll say is that there will be another preconfer after P3. So it might be P7, for example. And what the preconfer can say, if indeed they really have no more space available in their block, is say, I'm done with preconfing. If you want a preconfirmation, go talk to the next preconfer, go talk to P7, and give him this message saying, that P3 is done. So it's kind of a preconf chaining mechanism where you have the preconfs from P7 that are conditional on P3 settling its preconfirmations as it promised to its users.
Okay, there was one more question. Ralka, go ahead, please.
Yeah, so I just wanted to ask whether a proposer that has already been scheduled could basically renounce its role after issuing a preconf. And in that case, what would happen with the transaction that was preconfed in terms of scheduling, not in terms of penalties? And maybe a follow-up to that, if increasing the granularity of the Lookahead updates from epoch to slots would in any way help with predictability in the case proposers drop.
So the proposer, like, first, like, whether it's possible for like this preconfer to like be prior to preconfirmation and just say that, hey, I'm not going to be a proposer anymore. Like this is right now not possible because like they are already like scheduled for being a proposer for this slot, and there's not really like way to like say that, hey, I just don't want to be a proposer anymore and like I'll opt out. And this is especially the case like once we like have this EIP and like the proposer is like 100% deterministic. Like there's no way that like once you're allocated in a specific slot here that you like say that, hey, I don't want to be a proposer anymore. But like in a very, very like small edge case that we were talking about, it might be possible that like you're a proposer here and you provide preconfirmations and you say that I don't want to be a proposer anymore, and you like somehow change the effective balance in some way here so that you don't be a proposer anymore and like you can like not be such, for example. But and this is a very small edge case, and we're not even sure if this is possible. Like it's probably not, but it is a case to consider when we are thinking about undeterministic Lookahead that we have right now. And what this EIP does is it makes this part completely deterministic. So they completely like see that this is not possible. Like if you're a proposer, schedule a proposer, you're 100% going to be a proposer, and there's no way that you can opt out. So that's like actually another hidden like benefit of this EIP. Yeah, I guess like that's kind of like answered here because yes, this itself is not an issue. And if you have like Lookahead of like one slot, then yeah, preconfs would like be very hard to do because like you don't have the Lookahead and you don't know who the next opted in proposer is.
Thank you for sharing that. I know this is like very interesting session, very knowledgeable as well. But I would like to make it a little bit more fun for people who are watching this to know you more, to maybe know your views on Ethereum ecosystem. So let's move towards another section of this conversation, which is called Rapid Fire Round. In this round, what we generally do is try to collect answers from you in 1 minute or so. You can respond in one word or options if there are any. All right. Let's start with Lin. Your favorite programming language?
OCaml.
One word to describe your coding style: minimalistic, hacky, elegant, pragmatic.
I would want to be pragmatic, but sometimes I find myself trying to be elegant, not actually being elegant, but like trying to be elegant and failing.
What's the first thing you check in the morning? GitHub, Telegram, email, or Twitter?
Twitter.
Dark or light mode?
Dark.
Best part of working on Ethereum: community, innovation, open source, or freedom?
Community.
CLI or GUI?
Used to be CLI, but recently, because the AI editor is like much more GUI focused, so GUI.
A project you admire in the ecosystem?
Taiko.
And the last one here is favorite side project or hobby outside blockchain?
One side project that I have is Game Boy emulator. I write it in OCaml, and it actually runs in the browser. And yeah, recently I haven't been able to hack around it, but sometimes it's fun like working on it.
Thank you so much, Lin. I have my next set of questions for Justin. Your favorite EIP that is not authored by you?
I mean, I've only offered 2 EIPs. I guess I do like EIP-1559 that introduced the burn.
Yeah, one of the most popular EIPs. Well, my next question is a bit tricky. Vitalik in one word.
Genius, visionary.
The layer you love most? L1, L2, L3, all of them?
L1.
The next one is quantum computer in 2030. Yes, no, maybe.
Yes, but they won't break cryptography.
Where do you like to spend more time? Specs, podcast, research, or community?
I do enjoy podcasts because they're a forcing function. So when I get invited to a podcast, I usually mull over it for several days before the podcast. So I do spend a lot of time there. But I am looking forward to writing the Beam specs and spending a lot of time there as well.
Rollups are future. Yes, no, or too soon to say?
So this was actually, the content of some of my recent tweets. I think rollups are necessarily part of the future of Ethereum, just because the L1 is bottlenecked. The L1 EVM instance can only do so many transactions per second, because the EVM itself is kind of this single-threaded machine which has these sequential bottlenecks. So maybe we can push the EVM to 10,000 TPS, maybe to 100,000 TPS, but it seems very, very unlikely that we can get 1 million TPS, let's say. And the world just needs more than 1 million TPS. I think we need maybe closer to 10 million TPS, let's say. And the only way to provide that is through horizontal scaling. And I think this is where the L2s will play a role. And to try and quantify this, I believe that if we are to max out the L1 EVM and max out the L2s, the rough ratio will be roughly 1,000 to 1. So the L2s will provide 1,000 times more capacity than the L1. So I think the L1 is extremely important as a settlement layer, as a bridging layer, as a source of unified liquidity, as the sharding point for the shared sequencer, also as the sharding point for the execution. But ultimately, I think a lot of the activity will be on L2s.
Very well. My last question for you is favorite ETH event where people can follow you. Events which are organized by local ETH community like EthCC, ETH Denver, organized by Ethereum Foundation like DevConnect, DevCon, or organized by outside Ethereum community like CoinDesk.
Yeah, so I really like CCE, which is not very well known, is the Columbia Cryptoeconomics Conference. It's organized with Columbia University and the Ethereum Foundation, and it's very much focused around economics. I also very much like EthCC. The problem with EthCC is that there's so many events, and I get to run around the city like a headless chicken, so it's very exhausting. DevConnect, it's a similar vibe, and DevCon, I think, is one that I enjoy the most because there's not that many events, right? DevCon is the main event, and so I get to enjoy more of the content that's presented there.
Thank you so much for answering all these questions. We are heading towards the end of this conversation today. Is there any message that you would like to share from this platform?
I mean, in general, I'm a very, very optimistic person, and I guess I want to share a message of optimism that I believe the future of Ethereum is extremely bright in many, many different metrics. I think the whole story around preconfirmations are going to give us optimal UX, right? Something close to speed of light, close to ping latencies. I think we're going to be able to scale the blobs and scale the L1 so that there's capacity for everyone in the world, for the whole of internet finance. And I'm also hopeful that the traditional world of finance will migrate on-chain, specifically onto Ethereum. And we're talking tens of trillions, hundreds of trillions of dollars. And I'm also hopeful that Ethereum as a platform will be able to withstand the total value secured on top of it. In doing so, I think it will require large amounts of economic security, trillions of dollars of economic security. And so that means that the total value of the staked ETH has to grow. And ultimately, that also means that the value of ETH has to grow. So I've been in the space for about 10 years now, and I'm very, very optimistic to see how the next 10 years pan out.
Yes, I am optimistic as well. Yeah, let's hope that we have a brighter future ahead. Lin, I wonder if you would like to add something, how people can maybe able to support this proposal or anything in general that you would like to share from this platform.
Yes, like any support for this EIP, like we're aiming to be included in the next Fusaka fork, but it's still like in discussion. So if you're supportive of this, if you can raise a voice or something, that would be very helpful. And like actually very, very interesting writing an EIP. It was also my first EIP writing experience. And I actually had like kind of goosebumps when I was writing it. Like as Justin was mentioning, it's like the Ethereum is like the internet computer and the internet finance. And like being able to like write code, like it's not the actual client code that's going to be executed, but it's like the logic there, like is going to be included there and run there, I was like super cool. And I'm very, very honored to be able to like participate in this. So yeah, it was very interesting. And yeah, thanks Justin for like this.
Thank you, Lin and Justin. I'm sure I may not be able to help you with like your spec writing experience, but in case of EIP writing experience, if you face any challenges or any roadblocker there, we are happy to help. We do organize multiple meetings. One of them is called as EIP Editing Office Hour to provide support to new authors. And yes, if there are any questions, we would be happy to help you around that. Well, that's a wrap on our deep dive into EIP-7917. Huge thanks to Lin and Justin for sharing their insights. Viewers and listeners, be sure to check out the discussion thread and specs link in the show notes. Until next time, keep building the perfect ecosystem. This is Pooja Ranjan signing off. Thank you, everyone.